I'm about to guide you through LP graph formulation for operations research. And from the data we're given, we have the exterior paint, the maximum that's available for M1 and for M2. Then the profit we're given in this place. For exterior paint, we have 5, and that goes in thousands. This is 1,000 here, which was written in a small way, so sorry about that. Then the interior too comes in 4,002. So this is the data we're given. Then we have a constraint. The constraint that go with the data provided. For market study, we have interior paint cannot exceed exterior paint by more than 1 ton. Maximum daily demand for interior paint is 2 tons. Then now we are asked to find the optimal product mix to maximize total daily profit. How do we get the decision variables from here? Now that we have two type of paint, the exterior paint and the interior paint. So those ones form our decision variable. So all I need to do now is say our decision variables. So that will guide us to what we need to determine. So for X1, I will use X1 to represent tons of exterior paint. Then I will use X2 to represent tons of interior paint. So with these two, I've already stated my decision variable that I have X1 and X2. So the next step I'm going to advance towards now is how to state out my objective function. So to identify the objective function, I have maximize. So the objective function in this place wants us to find the optimal solution for the value that we got. So here I have 5 and 4 in tons, as in thousands of dollars. So I'll just say 5 for X1. So far X1 is tons of exterior paint. Then 5 multiplied by X2. That is tons of interior paint for paint 2. So what I'm going to have now is 5 X1 plus 4 X2. That is done. So the next step I'm going to move towards is to identify my constraints. My constraints, all this stuff is subject to what? So the first one is I have for M1 material, I have 6 for exterior and 4 for interior. Then the maximum available is 24. So I'm going to state that in this form, that I have 6 X1 plus 4 X2. Now because the maximum available is 24, I'm going to have an inequality sign that says lesser than 24 tons. Now what other objective do I have? I have 1 for M2 and 2 for interior paint, and I have maximum available. That's also a constraint. So I have X1 again plus 2 S2. I have a maximum of 6, so that will be lesser than 6. Now what other constraint do I have? We're told in this place that X2, that is interior paint, cannot exceed exterior paint by more than 1 ton. So in regard of that, I will put my X2 interior paint minus exterior paint to be lesser than 1. That's another constraint. Minus X1, that is lesser than 1. Then I have other constraint that says maximum daily demand for interior paint is 2 tons. That is the maximum. So if that is the maximum, then I cannot have it higher than that. So it's going to be lesser than. So what I'm going to do is to say X2 is lesser and equal to 2. So then I have my non-negativity constraint that says X1, X2 must be greater than 0. With this, I've been able to clearly state out my constraint. So from there, I can now advance to plotting the graph for the question that has been given. So as I advance, I have a makeshift graph paper I'm going to use in this place. So by looking at this, one method you could use that could help you very fast to put these values, because we're going to use the constraint to make our graph. So a method that will help you to get them on the graph very quickly is to say when x1 is 0, what will you have for x2, and when x2 is 0, what will you have for x1. So in this place, when x1 was 0, then x2 is going to give me 6. So on this graph, x2 is going to be on this part, while x1 will be represented on the x-axis. So as you can see, I have to represent y-axis with x2, and x-axis I have to represent that with x1. So with this, I can now conveniently put this back on the table. So for the first constraint that we have, I will say that when x1 was 0, then x2 will be 6. So on this place, I will stay on 6. And when x2 is 0, x1 will be 4 by, putting this on this side, and I have 4. So on the two sides, I'm going to plot this down 6 to 4. So that is the graph for the first one, 6 to 4. Now for the second constraint, if I say when x1 is 0, what will x2 be? So 2 divided by 6, that's 3. That means my x2 is going to be 3. Then when x2 is 0, x1 is going to be 6. So my x1 here is going to be 6. So I have 3 to 6. So the next thing in the constraint to see, I have x2 minus x1 is lesser than 1. x2 minus x1 is lesser than 1. So if x1 is 0, then x2 is going to be 1. So in this place, I have 1. Then if x1 is 0, then x2, if x1 is 0, the x is going to be 1. If x2 is 0, x1 is going to be negative 1. So in this place, I'm going to have negative 1 and 1. So that's going to be, and it's beginning to take shape. So the next constraint that I have says x2 is lesser than 2, just like saying x2 equals to 2. So on x2, I'll make a straight line that goes straight down. This is that we're drawn on this graph. So, and this is where they intersect, and now made an enclosure, something like a portion, and that's what they call the feasible region of feasibility, where the point gave us, and this area is the point where you have the feasible solution for the maximization of the profit. So, and what I need to also do is to get the values for the point that made the boundary in this place. So here I have 4, 0. When x was 4, when x was 4, y was 0. And here I have 3, 1.5. Here I have 2, 2. Here I have 1.2. 1 and 2. Here I have 1 and 0 and 1. Then I have, at this point too, I have 0 and 0. You can see that very clearly now. So that's what I interpret to be. If I produce 3 tons of interior paint and 1.5 tons of exterior paint, I'm going to make a profit of $21,000. So out of the 4 points that we have here, this region gave us the best possible feasible solution that we desire. So if you love this teaching segment, you can subscribe on my channel. God bless you for watching. Thank you. Bye.